Hey guys, I just wanted to go over some torque problems with you. These are going to be rotational as well as linear equilibrium problems, which means that F net will be equal to 0 as well will be the sum of the torques. So a meter stick is balanced at the 50 centimeter mark. So right in the middle. A 0.5 kilogram block is located at 40 centimeters. So that would mean that the block is here. That would be 0.1 meters from the fulcrum. If this is 0.5 kilograms, that is a 5 Newton block. Where should a 0.2 kilogram block be located to balance the meter stick? So somewhere on this side, my 0.2 kilogram would be 2 newtons. And I don't know what R is. All right, so I am saying that the sum of the torques is equal to 0 because it is not rotating. And so that would mean that my torques that are going counterclockwise are equal to my torques that are going clockwise. Remember, torque is the cross product of the radius and the force, or you can write it as RF perpendicular. Our radiuses and our forces are perpendicular in this case. So the counterclockwise ones, the ones that want to make it go this way, is going to be 0.1 meters and 5 newtons. My clockwise torque is going to be provided by the 2 Newton block. And so I'm going to have 0.1 times 5 divided by 2. And so that tells me that R is equal to 0.25 meters, which means that it is 0.25 from 50 centimeters, so it would be at the 75 centimeter mark. All right, I'm going to clear the ink. This is a common problem as well. A 50 kilogram, 20 meter plank is extended 8 meters over a ledge. How far can a 100 kilogram man walk out on the plank before it tips? I need to determine my fulcrum. And in this case, I would say my fulcrum is where the board meets the edge of the ledge. So if he gets too far, this is going to go that way. I know that for a 20 meter plank, I can consider all of the mass to be at 10 meters. So there's 12 meters of it before there. And so that means that the weight is here. And this distance would be 2 meters. So if the whole thing's 20 meters, and I'm saying all of the weight is acting there, a 50 kilogram plank is going to be 500 newtons acting at that point. That's 2 meters away from the fulcrum that I picked. How far can a 100 kilogram man, so a 1,000 Newton man, walk out on the plank before it tips? I want to know what this distance is, which we would call R. His force is going to be 1,000 newtons. And again, we're saying that this is in both rotational and linear equilibrium. So the sum of my torques is equal to 0, the sum of my forces is equal to 0. So I would take my torques that are counter equal to my torques that are clock. My counterclockwise torque is going to be 2 meters times 500 newtons. Again, these are perpendicular. My clockwise torque is going to be R, how far we are from the ledge, multiplied by the weight of the man. And it looks like I have 2 times 500 divided by 1,000. And he could go out 1 meter. At 1 meter, he would still be balanced. If he went any further than 1 meter out, the plank would start to tip. All right, I'm going to clear the ink. A 2 Newton meter stick is suspended by string at each end. So now my meter stick is it has strings that are holding it up at each end. A 6 Newton pineapple is suspended 0.3 meters from the right string. So here's my pineapple. And we're saying that this pineapple is 6 newtons. Its distance from there to there is 0.3 meters. So it is as a force that's going down. What is the tension in the right string? Okay, so we have a number of tensions here. We have the tension in the left string that is going up. We have the tension in the right string that's going down. We have the weight of the pineapple that's going down. And we also have the weight of the meter stick. Where is the weight of the meter stick going to be concentrated? In the middle. So at the 50 centimeter mark, I'm going to have 2 newtons. And that's going to be 0.5 meters from either string. I'm going to assume that my meter stick is uniform. All right, so I'm going to balance these forces and this torque. First thing is I need to decide what my fulcrum is going to be. If this system were to fail, one of 2 things would happen. One, this string would snap and the whole thing would swing this way. 2, this string would snap and it would swing this way. Since I want this tension, I'm going to make my fulcrum this point here. If I wanted TL, I would do the opposite. I can do either one. And so I'm going to say the sum of my torques is equal to 0. So I'm going to take the torques counterclockwise equal to the torques clockwise. So counterclockwise would be this way. The only torque is the tension in the right string. That is 1 meter from the other string. So that's going to be 1 meter times the tension in the right string. This is going to be equal to my clockwise torques. It's going to be 2 newtons times 0.5 meters. So I'm going to consider all of the weight of the meter stick to be acting at 0.5 and the weight of the watermelon times how far it is from the fulcrum, which is going to be 0.7 if it's 0.3 from this one. So that's going to be 0.7 times 6. And so the tension in the right string is going to be equal to 0.5 times 2 would be 1. 0.7 times 6 would be 4.2. So it would be 5.2 newtons. I also know that F net is equal to 0. So that means the forces up have to equal the forces down. I have 8 newtons of force down. I have a pineapple, and I have a meter stick, and I have 5.2 going up at this point. That means I have to have 2.8 going up at the other side. I just wanted to clear the ink.